Well friends, in the earlier module, we have discussed about various types of physical quantities, their classification as vectors and scalars, units, dimensions and many other important properties which are very much important for a beginner in the field of electronics. The person who is studying electronics for the first time, for him all these things will be quite useful. Another requirement in physics is how to represent these physical quantities. So, representation of a physical quantity is another issue, and for that purpose we have to suggest some mathematical model, because we can see many things, we can observe, but how to describe them mathematically. For example, if a question is asked, where is lamp in the hall? To answer this question, we will raise our hand and we will say that the lamp is there. Okay, the lamp is there, that is fine, but how to represent it mathematically? So, for that purpose we have to use some mathematical tool. If a question is asked that a stone is thrown like this, how it will move? We say that it will move like this. Okay, fine, but how to represent it mathematically on the paper? If a question is asked that electron is moving in the electromagnetic field, how it will move? Then we can say that it may move like this, fine, but how to describe it mathematically? So, we need to develop or we need some help of mathematical tool for representation of all these physical quantities. And that is why we are going to study some important mathematical tools which are important in the study of electrodynamics. Whenever we talk about representation of a mathematical quantity or a physical quantity in terms of mathematics, the question arises that what exactly we are going to study in the subject. As far as electrodynamics is concerned, we should ask ourselves, what is electrodynamics? What we are studying? The answer is very simple. In electrodynamics, we study about motion of charged particles in different environments and the related applications of it. Whenever you talk about environment, you will ask the question, sir, what is environment? Yes, you are right. There are many aspects associated with the term environment. One of the important aspects associated with environment is that we have to search whether there exists any symmetry in the problem under consideration. You will ask the question, what is symmetry? Yes, whenever I talk, such questions are bound to occur in your mind, and that is a very good sign. So, what is symmetry? If you look around the nature, you will find that there are many types of symmetries. You will ask the question, what is meant by symmetry? All these things will be discussed in this module. But if a problem is having symmetry, yes, I would like to say one thing about symmetry. It is a very famous statement, nature loves symmetry. Nature loves symmetry. Fortunately, in electrodynamics, in most of the problems, there is some type of symmetry. If the problem is symmetric, then it can be solved very easily with the help of a mathematical tool which is known as coordinate systems. You will ask the question, what is meant by coordinate system? Yes, again questions. In my opinion, whenever we ask or whenever we study some new concept or new subject in science, we must have a habit of asking questions. When the questions are raised, then somebody has to answer, and any attempt to answer such questions or rather finding answers to these questions will definitely help in understanding the subject to a better extent. That is why question must be asked. As far as this subject is concerned, you will ask the question, okay, coordinate system, what is meant by system, what is meant by coordinates? All these things are very important. You will ask the question, symmetry, what are the examples of symmetry? My dear friends, please look around the nature and you will find number of symmetries. Those examples we will see in this module. I hope you will enjoy studying or looking at those. Now, another thing is that whenever we want to solve any problem, we have to use some mathematical tools. So, we must be aware that what are the different tools. In this module, we are going to talk about some important terms. For example, coordinate axis, unit vectors, their properties and so many other things. Whenever we ask ourselves, have you really understood these terms? Can you explain it to the others? Yes, if you can explain it to the others, then you have better understood the subject, and that is why we have given some importance for understanding the concepts visually as well as numerically. As far as symmetry is concerned, as I already mentioned, in the nature there are too many symmetries, lot of symmetries, but we are not going to study all. We are going to restrict our discussion to the planar symmetry, rectangular symmetry, circular symmetry and spherical symmetry, because these are direct concern in most of the problems in electrodynamics. And I hope you will agree, that theory is better understood with the help of illustrations and numerical exercises, and that is why at the end we will study some examples and illustrations so as to understand some important mathematical computations needed for electrodynamics. This module is aimed at study of some important aspects of coordinate system and will be useful in understanding special features of the different types, unit vectors and their properties. An introduction of the topic in this module will serve the purpose of development of a basis for theoretical understanding of electrodynamics. In my opinion, it is always better to get familiar with meaning of some important words used in any concept, title, phrase, etc. For example, we use the words physical systems and symmetries. What is meant by system or physical system? Such questions must arise in our mind. A little thought will make you able to answer. We know a simple pendulum. We might be interested in deriving a formula for its time period. One may be interested in knowing the time needed for a wooden block in moving down an inclined plane through a specified distance under the action of gravity. All such are the examples of physical systems. We may describe a physical system as an object or a group of objects, the properties of which are under investigation. As an exercise, will you try to name 10 examples of physical systems? Well friends, please note that 2x plus 3y equal to 13 and 5x plus 4y equal to 22 is a system of two simultaneous equations. It is a mathematical system and should not be confused with physical system. We may think over the terms biological systems, chemical systems and so on. How pleasant and beautiful is the life of fishes. Just observe two more pictures. What do you note? Have you noted the shape of the fish tank in each of these four cases? Can you imagine electrons moving instead of fishes in such enclosed containers? What are the things which we might be interested in knowing about such systems? Think for a moment and you will note that given a physical system, we are interested in knowing about the general features of static and dynamic behavior of the system and analysis of associated phenomena. In general, we are interested in study of quantitative, qualitative and applied aspects related with system. Careful observation and search for symmetry, if any, are highly useful for extracting useful information about a given physical system. Let us have a look at some of the examples. Let us have a look over the symmetrical aspects in the contents of the few slides which follow. Do you observe anything common in all of them? Would you like to play with a carom board? Here we have a bead moving along a horizontal ring. Remember, even wall clocks have hands. I am sure you must have solved problems with a ball rolling down an inclined plane. Now, Here is a system of 4 charge conducting spheres held fixed on the smooth horizontal surface of a table. A tiny bead with positive charge plus q is kept near the first spherical conductor with charge plus q1. When made free, how the bead will move on the surface of the table under the action of attractive and repulsive forces? Let us see. Observe the motion. Thus, the overall motion of the tiny charge will take place somewhat like this. Needless to mention the fact that all these examples bear planar symmetry. The motion is in the plane. Now, let us see some examples of rectangular symmetry. Here we see a butterfly flying in the hall and the fishes swimming in the water tank. In both of these illustrations, the motion is confined to a region in the form of a rectangular parallelepiped. Another type of symmetry is the cylindrical symmetry. Coaxial cable used for transmitting the electrical signal is a well-known example of it. Cylindrical waveguides used for transmission of high-power electromagnetic waves is another famous example having cylindrical symmetry. The problem of determination of magnetic field due to a straight, infinitely long current carrying conductor is familiar with us. It also involves cylindrical symmetry. Can you think of some more examples? Many examples can be given representing spherical symmetry also. Electric field lines due to a point charge in space is the simplest and most familiar example of it. An electron moving around the nucleus of an hydrogen atom or a particle moving along the surface of a sphere are the systems having spherical symmetry. It be remembered that many other symmetries also exist. As a simple example, we may think of electrons orbiting around the nucleus of an atom or a planet moving around the sun, or fishes swimming in an elliptical tank. These are representative of physical systems having elliptical symmetry. Search for some more symmetries and examples therein as an exercise. Have a habit of asking questions to yourself. Think over some of such questions raised in connection with symmetries. For example, what are the other types of symmetries? Is it necessary that every physical system must have a symmetry? Can you give an example of a system having no definite symmetry? So far, we have seen examples of different types of systems and symmetries. The question now arises is that of representing different physical systems having a given symmetry. Can we think of a mathematical tool for this? The answer is yes. For numerical or graphical representation and analysis, we can think of a mathematical tool called coordinate system. Obviously, one may ask the question, what is coordinate system? A smart way of answering is, it is a system of coordinates. Okay, then my question is, what is meant by coordinates? To get the answer to this question, let us take a simple example of locating the position of a fan in your house. Where is the fan? It is easy to understand that mere mention of its height from the carpet in the hall or its distance from either of the walls will not be sufficient. Rather, the mention of only 3 distances is sufficient to specify the position of the fan exactly. Which are they? What are the reference planes, lines or directions used for measurements? We call these distances as coordinates of fan. The minimum number of physical quantities, remember what I am saying, the minimum number of physical quantities required for specifying the position of the system are called as coordinates of the physical system. Any real world object can be described using a coordinate system. The reference directions used are called as axes and the numerical measurements made as coordinates in that system. Let us consider an object lying on a horizontal table represented by a point P in the plane. Where is the point P? To answer the question, we may select two lines OX and OY on the plane surface of the table. Then the answer is P is at a distance of 12 units from the line OY and at a distance of 5 units from the line OX. It is not necessary to mention that it is at a distance of 13 units from O. The reference lines OX and OY chosen by us are known as coordinate axes and the distances 12 and 5 are known as coordinates of the point P. Thus, the coordinates of point P will be x equal to 12 and y equal to 5. We can give many such examples which are much more familiar to us. Depending upon the symmetry, we have different types of coordinate system. The commonly used systems are polar coordinate system, rectangular coordinate system, spherical coordinate system, cylindrical coordinate system. In this module, we are going to restrict our discussion only to these four commonly used coordinate systems. To start with, let us discuss about a simple system known as polar coordinate system. Let us suppose that the points O and P represent the observer and the object to be observed respectively. Consider two straight lines mutually perpendicular to each other and passing through point O as reference lines. The distance r is equal to OP and the angle theta measured in the anticlockwise direction from the positive direction of the line OX will be sufficient to describe the position of point P with respect to O. Here r and theta are called as polar coordinates of point P. A simple trigonometrical considerations can give the relation between r, theta, x and y as shown. The point O from which the distance r is measured is called as pole. Now, let us discuss about the other system, namely rectangular coordinate system. As before, let P be the point to be observed by an observer O. A set of three mutually perpendicular straight lines passing through O represents the coordinate axis. It be noted that this system is also referred as Cartesian coordinate system in the name of great mathematician René Descartes. Draw lines Pn, Pl and Pt from P perpendicular to the lines OX, OY and OZ respectively. Then the distances OX is equal to x, OY is equal to y, OZ is equal to z represent the coordinates of the point P in this system. Note that point P will be at a height Pm is equal to z from the xy plane. With constant values of x, y and z, we get three different planes as specified. For example, with x equal to constant, we obtain a vertical plane parallel to yz plane at a distance x from it and so on. In spherical coordinate system, the coordinates are r, theta and phi as shown. In this system, for constant value of r, we obtain a sphere of radius r, while constant values of theta and phi generate a cone and a vertical plane respectively. Relation between coordinates of a point in rectangular and spherical system can be obtained using simple trigonometrical manipulations. In the last coordinate system, namely cylindrical coordinate system, the coordinates of point P are rho, phi and z. Rho is the distance of point P from z axis, z is the height or depth of P from xy plane and phi has the same meaning as that in spherical coordinate system. Here rho equal to constant generates a right circular cylinder, while constant values of phi and z generate planes. Relation between coordinates of a point in rectangular and cylindrical system can be obtained using simple trigonometrical manipulations. We must note the ranges of the coordinates in different systems. The coordinate theta is also called as polar angle, while phi is many a times called as azimuthal angle. Note that the angular coordinates theta and phi have finite ranges, while the coordinates rho, phi and z have infinite range. Now let us discuss about a simple but important concept known as position vector. Consider a ceiling fan in a hall. There are two observers in the hall. When asked, the first person points his hand towards the fan as shown. On the other hand, the second person points his hand in some other direction as shown. Thus, the description of the position of the same fan as described by two persons can be different. Who is correct in describing the position of the fan? We understand that both persons are correct. Description of the position of the object to be observed depends upon the position of the observer. The observation point P in electromagnetics is many a times called as field point, while the observer O is referred as a source point. Remember that position vector of a point is a vector drawn from the observer to the observation point. Thus, OP bar is the position vector of point O with respect to O. It is a vector drawn from the observer O to the observation point P. In the case of a system of 3 points, say O, P and Q, the position vectors of one point with respect to the others will be as shown. Oh, let us welcome a beautiful butterfly entering our classroom to charm us and give energy to study further by looking at it. See how the position vector of the butterfly is changing with time t. One can get the trajectory of its flight as shown with the help of position vectors at different time instants, or rather successive time instants. The knowledge of position vector of an object is very important in physics. From position vector R, we can determine all other physical quantities in mechanics using mathematical tools. For example, if r bar t is a position vector of a particle, then the time derivative of r bar gives velocity v. One more differentiation gives acceleration a bar, which on multiplication with mass gives force F bar. Scalar product of force and displacement gives information about the work done. The work done remains stored in the particle as its energy. Time rate of change of work done gives power, which can be related with prediction of efficiency. In the earlier module, we have seen the definition of a unit vector. Position vector, say p bar, can be expressed in terms of its magnitude and the unit vector along it. It be noted that in literature, different authors use different symbols to represent coordinates in different coordinate systems. Similarly, the unit vectors are also represented in a variety of ways. Let us have a look at it. For present discussion, let us adopt the symbols for unit vectors in different coordinate systems as shown. Let us see how the unit vectors along the corresponding coordinate axis in different coordinate systems are represented diagrammatically. In polar coordinate system, the vector r bar itself indicates the r axis, while the tangent to the circle of radius r at point A drawn in anticlockwise direction represents theta axis. The unit vectors along these axes are as shown. Axis for r bar is the position vector r. The theta axis is along the tangent to the vertical circle at point A drawn in the increasing direction of theta, while The phi axis is along the tangent drawn to the circle at point A in the increasing direction of phi and parallel to xy axis. In cylindrical coordinate system, the axis for rho is the vector drawn from z axis to the observation point perpendicular to z axis. The phi axis is the same as that in spherical coordinate system. The z axis is a vertical line through P parallel to z axis. The unit vectors along the three axes are as per the definition. Any given vector, say A bar, can then be written in terms of the components of A bar along the coordinate axis and the respective unit vectors as shown. As per the definition, scalar product of a unit vector with itself equals unity, while that of two dissimilar unit vectors vanishes. The vector product of two unit vectors has obviously unit magnitude with direction as per the right-handed screw rule. It is worthwhile to note that unit vectors in Cartesian coordinate system are constant vectors. Unit vectors in polar, spherical and cylindrical coordinates, on the other hand, are in general not constant vectors. Rather, they are variable position dependent unit vectors. As an example, observe the unit vectors at two different points A and B in polar coordinate system. While solving problems in electromagnetics, we need to evaluate line integrals, surface and volume integrals. The work done in displacing an electric charge, the electric flux phi through a surface and total electric charge enclosed in volume V are some of such examples. For this, we must know the expressions for line element, area element and volume element in different systems. The line elements are as shown. Note the unit vectors indicating the direction of line and area element in each system. Volume elements are scalars while other two are vectors. How to obtain these expressions? For understanding the concept, imagine an infinitesimally small closed volume in the form of a parallel pipe such that length L, breadth B and height h or depth h viewed at each corner are mutually perpendicular to each other. Then area element ds is given by the product of the two, namely ds is equal to L by L into B, L into H, B into H numerically, associated by appropriate unit vectors as per the vector product rules, and volume element dV is equal to L into B into H. Simple trigonometrical manipulations can give the values of L, B and H in the desired coordinate system. The diagrams which follow will be useful in deriving the different expressions for volume element and surface element in different coordinate systems under consideration. One more important concept is direction cosines. These give information about the inclination of a given vector with positive direction of x, y and z axis. At the end, let us get familiar with some computational aspects with the help of few numerical exercises. Consider problem number 1. Given a vector, determine its inclination with x, y and z axis. Definitely, the problem is pertaining to direction cosines. We need to know magnitude of the vector and its components. The vector has magnitude 7.071 unit and has x, y, z components as 3, 4 and 5 respectively. Using these values, we can compute the angles alpha, beta and gamma as shown. When the coordinates of 2 points say P and Q are given, the magnitude of the vector PQ bar and QP bar can be determined using distance formula in trigonometry. The problem is representative of this point. Now, let us see a problem wherein the knowledge of computing components of a vector along a specific direction is involved. The problem reads like this. Consider an electromagnetic wave incident at a point on the plane boundary of two dielectrics with its electric field vector of strength E volts per meter inclined at an angle theta with the normal to the surface. Find the components of electric field parallel and perpendicular to the surface at the boundary. The figure is self-explanatory about the situation described in the problem. MP is the component of electric field normal to the surface at the point of incidence P, while NP is the other desired component parallel to the surface. Note that this problem is useful to understand the derivations of boundary conditions on the vectors B, H, E and D in electromagnetics. Dear friends, to summarize, we can say that depending upon the symmetry of the problem, we can analyze the situation using a proper coordinate system, either polar, rectangular, cylindrical or spherical. Unit vectors in different coordinate systems have different properties. Especially the unit vectors in Cartesian are constant vectors. In all the other remaining coordinate systems, they are not constant vectors, they depend upon the position of the observation point. Different authors, they use different symbols for unit vectors as well as the coordinates of the point in different coordinate systems. Position vector is one of the important vector which is to be studied properly, because from position vector we can derive all other physical quantities simply by using mathematical tools like derivatives, integrals, etc. Okay, then friends, another point is that the knowledge about trigonometry, which we have already studied at earlier stages, can be used to derive the relations between coordinates of a point in different coordinate system. With these words, I think we will conclude. Let us see once again to discuss some advanced topics like divergence, curl, gradient, etc. in the next module. Thank you.